from University of Liverpool, where he dabbles in computer science, but he's a legendary Rubik's Cube, the former student at Yale.
Thanks, Arkadev. Pleasure to be back in TIFR. So what I'll be talking about today is joint work with Manasvi, Swagato, and Nitin. Swagato also was at TIFR until 2017. Also visited a few weeks ago, I think. As you can see, I don't have too many slides, so I hope to keep this interactive. Just interrupt me if there's any questions and so on.
Use that if you want.
Sorry? So I will use the board for a bit of stuff. But yeah. Right, so the title is slightly different from what was advertised in the abstract, but I will be talking about on communication complexity of finding tournament winners. And we'll come to definitions and all soon enough. So to begin with, I'll be telling you what tournaments are, what is this notion of kings in tournaments. Very briefly, I'll describe the setup of communication complexity that's relevant to us. At this point, I'll tell you our results and some sketches of proofs and so on. And then I'll summarize. Again, please interrupt me at any point if some things are clear. All right, so to begin with, what are tournaments? So a tournament is a complete directed graph. So that means you have a graph on n vertices. In this case, n is 5. And there's a direction between each pair of vertices. So you have a complete graph on n vertices and a direction between each pair. And what you should think of this as is each vertex being a player in a, let's say, sports tournament. And an edge directed from Vi to Vj indicates Vi defeated Vj. Right? So it's a round robin tournament where every team plays each other exactly once. And there's no ties. So it's just win or lose. So for instance, here we have V1 defeats V2, V4 defeats V2, and so on. And what's going to be of interest to us today is going to be how do we find or can we find a winner in a given tournament? So before we start answering this question, we first have to realize that there's no clear definition of what is a winner in a tournament. Okay? So in what case is there a clear definition of a winner in this case? So let's say there is a vertex or there is a player who defeats everybody else. Now this fellow is clearly undisputed winner of the tournament. So in other words, if there's a source in this tournament, then you should be declaring that person as the winner, or that vertex as the winner. But if you think about it soon enough, you'll realize if that's your definition of a winner, it need not be the case that there's always a winner. So for instance, in this tournament, unless I made a huge mess in LaTeX, I mean, this shouldn't have a source. All right, so now that brings up the natural question, like, can we generalize this notion of source being a winner in a suitable way? And so that brings us to the definition of a king. And this notion was defined by Landau in the early 50s. I'll reference him soon. Landau was not a computer scientist. He was a mathematical biologist or a sociologist. And the title of his paper was, I might not get it exactly right, but it's effectively on dominance structure relations in animal societies. So his motivation was, let's say you have a flock of chickens and then each of them fight against each other. So there's a certain pecking order between chickens. And chicken A defeats chicken B is represented by an edge from A to B. And his goal was to study how do you determine who is a most dominant chicken. So this appeared in the Bulletin of Mathematical Biophysics. So this is not a computer science notion originally. All right, so let's come to the definition. A vertex V is a king if for all other vertices, W, either there's an edge from V to W or there's a length 2 path from V to W. So in other words, vertex V is a king if it 2 dominates all other vertices. I'm being a bit vague here, but this is the formal definition. So again, a vertex V is a king if every other vertex can be reached from V via a path of length 1 or 2. So this is a natural extension of the definition of a source, or a relaxation of the definition of a source. Instead of one domination, you ask for two domination. So the first question to ask is, yeah, okay, good. So does there exist a king in a tournament always? And the answer is yes. And Landau proved this in the paper where he introduced the notion. What I'm going to do is I'm going to use the board to at least give a proof by picture. There will be a formal proof up here for those who are interested. So consider a tournament and let's consider a vertex V that has maximum out degree in this tournament. And I'm going to claim that this vertex, so suppose V is a vertex with maximum out degree. There may be several such vertices, pick one arbitrarily. I claim that this is a king. So towards a contradiction, suppose this is not a king. That means there is another vertex W that is not two-step dominated by V. So in particular, there is no edge from V to W. That means the edge between W and V must be in this direction. Also, there is no length 2 path from V to W. So that means all edges here also must be in this direction. So then if you count the out degree of this, you have D from here and 1 from V. So that's a contradiction, and therefore V is a king. Yeah, if you want a formal proof.
The problem is there will be many kings. Right?
Yes.
You still don't have a winner.
That's true. So, oh, winner, right? I mean, you can have multiple winners. Yeah, I mean, there's been a lot of study on how you define winners in like social choice theory and so on. I'm not very familiar with that side of things. Our focus is just going to be kings and sources for today. You're right, there may be several winners.
You can see in the team graph, the individual subgraph of each cell we have a team.
Sure. But they could all be kings, for instance.
Yeah.
Then you'll never reduce.
I think this is what we call Copeland inversion.
This possibly. Yeah, so I'm not aware of the voting theory, social theory side.
What Copeland?
Copeland winner.
Maximum.
We can look it up later. Okay, so at least the natural extension of source, that's the notion of a king, ensures that there's always at least one winner in a tournament. Right, so the setup that Alright, so now that we know that there exists a king, the question is, can we find one efficiently? Right? And the setup or the model of complexity in which we're going to do this, in which it's been more studied, is the setting of query complexity, which I'll describe now. So the algorithm that you're designing knows the number of vertices or the numbers of players in the tournaments. And to begin with, all edge directions are unknown. Thanks. And what an algorithm can do is it can choose a pair of vertices, and at unit cost, it can say, give me the direction between this pair. So let's look at an example. So to begin with, this tournament had 5 vertices. The algorithm knows that. And let's say in the beginning, it decides, I want to know who wins in the game between V1 and V2. And they spend 1 cost here, and they're told that there's an edge from V1 to V2. Now, the algorithm can make internal decisions based on this result, but this is all treated to be free. So the only cost is the number of times you're querying this tournament for an edge direction. So the algorithm may now think, okay, I want to know the edge between V1 and V3. What's the direction? They're told that this is the direction and so on. And the algorithm will keep making queries in such a way until it can definitively output a king. So in this case, the algorithm here will output the vertex v4 or can output the vertex v4 because it sees that v4 dominates v5, v1 and v2 directly, and it also dominates v3 either via v1 or via v2. So it doesn't need to query the remaining edges. So the cost of an algorithm, as you can expect, is the number of queries made by the algorithm in the worst case. Any questions so far? All right, so some known results about finding kings in tournaments. Like we proved on the board here, a vertex that has maximum out degree is a king. So if I want to find a king, you may ask, fine, let's just find a vertex of maximum out degree. But there's a fairly early result that shows that this would require you to essentially query the entire tournament, all edges in the tournament. So can we do better than this? And the answer is actually yes. There's a work of Shen, Sheng, and Wu from roughly 20 years ago, who devised an algorithm of cost order n to the 3 over 2. So note, this is n-vertex tournaments. So you have theta n square many edge directions. Right? So you can actually find a king in polynomially smaller number of edge queries. And this proof is fairly simple. I mean, if we have time, we could even go over it later. They also showed a non-matching lower bound of omega n to the 4/3. And despite quite a lot of research in this area, this is state of the art. So I think this is a cute problem. It should be easily solvable. It's just not been solved yet. But there have been works looking at variants and so on. So some of these works are, let's say, instead of finding a vertex that 2 dominates all other vertices, you just want a vertex that 2 dominates half of the other vertices. So this can be done in query complexity order n to the 4/3. This half was generalized to 0.618 2 years ago. But now, if you actually want to find a king that 2 dominates all other vertices in the, but you allow for randomized or quantum query algorithms, we studied this last year. And there it's much easier to actually show tight bounds. So we are matching upper and lower bounds in this case. So if you want to find a king, the key lemma that is used in most of these algorithms that find an exact king is due to Maurer. There's a lot of notation here, but again, I'm going to switch to the board in order to define the notation. But first, I'll say a few words about Maurer's paper. So from the early 50s until Maurer's paper, there was not too much work on tournaments and so on, but this popular science article by Maurer really sparked the interest again. So Maurer wrote an article in the Mathematics magazine. It's actually called the Mathematics magazine. And the title of the article is The King Chicken Theorems, where he also introduced, basically rekindled the interest of tournaments and solutions to tournaments, kings in tournaments, and so on. It's a fairly fun read, both this and the earlier paper of Landau. So I recommend taking a look at it. These are popular science articles. All right. So I've condensed quite a lot of text onto this statement here. Consider an arbitrary vertex V in a tournament and consider all of the vertices that have an edge pointing to V. I'm going to call this set the in neighborhood of V, or n minus V. And everything else is the out neighborhood of V. So the lemma states that for an arbitrary vertex, if you look at its in neighborhood, you look at the tournament induced on these vertices. So just look at the edges between these vertices here. A king in that tournament is a king in the original tournament as well. And let's very quickly see a proof. So let's say I have a vertex here, let's call it K. That is a king in the tournament induced on n minus v. So K two-step dominates everything over here. K has a direct edge to V because it's in the in neighborhood of V. And via V, it two-step dominates everything over here. So if K is a king over here, then it's a king in the entire tournament. This is proof. And now, once we have these lemmas, it becomes a natural approach. I mean, let's try to find a vertex of high out degree. Eliminate its out neighbors, just zone into its in neighborhood and recurse. And that's what most of the algorithms for finding kings actually do.
Wait, but you said theta n. You're ignoring log factors, but it seems like theta log n. N log n.
Where?
In the theorem, you said theta n, but
Here,
yeah.
for randomized.
Yeah, this one seems like theta n log n because you remove half every time.
Or
maybe
yeah, but yeah, you can get some geometric sum. So I pick a random vertex with yeah, so you do some careful error, either do some careful error analysis or you get some geometric sum type thing. In quantum, unfortunately, it's not so clean. I mean, most of our work here was like polishing up the technical details for the quantum setting. We lose log factors. Right. Any more questions so far? Right. Okay. So most of the work that's been done so far is in the setting of query complexity. In this work, we looked at finding kings and sources from the context of communication complexity. Not
for the query complexity, the step is still there.
Yes. That's unfortunate. Still there. Fortunate. Right. So we look at it from the context of communication complexity, and it's not just purely out of intellectual interest. I'll also I'll show you some connections with some well-known communication complexity problems as well. So in the usual setting of communication complexity, there's that we care about today, there's two parties, Alice and Bob, and they have some known function capital F that they wish to jointly compute. And the input to this known function is split between two parties, Alice and Bob in this case. So Alice sees her entire input, but not Bob's. Bob sees his entire input, but not Alice's. And what they can do in order to compute this F is they can communicate via some protocol pi, which they've a priori agreed upon. So how does the protocol work? So Alice can look at her input X. So based on X and the function, she can send a message M1 to Bob. Then Bob does some internal computations, which are treated free. So again, all internal computations by Alice and by Bob are treated as free in this setting. So Bob, based on his input and the message he received M1 and also the function he replies saying M2, and then they proceed thus until they agree upon an answer. And the correctness requirement here is that the answer must be correct regardless of what input you started. So it's a correctness requirement everywhere. There's no security issues. These channels are not noisy. So this is Yau's model of communication. The cost of a protocol is the number of bits communicated in the worst case. So in our setting, what does this mean? So in our setting, it's slightly different. So in the communication complexity setting that we consider for tournaments, there is some underlying tournament. Some of the edges Alice has access to and some of the edges Bob has access to. So for instance, this might be Alice's view. So she has some of these edges. And this might be Bob's view. And if you superpose them on each other, you get the entire turbine.
There is no overlap.
You could assume that there's no overlap, I guess. So they know in advance, let's say, which edge sets they're getting.
Once you get the edge, they know what other edges there will be at the person.
Yeah. But if, I guess you could say, like, what happens if,
Just overlap.
yeah, and I don't know, maybe that the other player has overlap. I'm not sure. Somehow that's not natural, at least for me. Right. So in this setting, some edges are with Alice, some edges are with Bob, and these are disjoint. And when you superpose them on each other, you get the entire original tournament. And their goal is to find either a source or a winner in this tournament. And they want to again minimize the number of bits communicated between them. So how do we find a king here? So what we're going to do is we're going to use this lemma by Maurer that says if you can find a vertex of high out degree, eliminate its out neighborhood, recurse onto the in neighborhood. And we're going to implement that over here. It's not a very hard protocol. So to begin with, let's assume without loss of generality that Alice has at least half of all of the total edge directions. So just by a counting argument, this means that she must have a vertex that has out degree at least n-1/4, because the average out degree of her vertices is n-1/4. This should be out over here, apologies. So what she does is she just sends the label of this vertex to Bob, which is log n bits. And along with this, she also sends the entire in neighborhood, out neighborhood, both works because it's the same thing again. Let's replace in by out both here and here. So she sends the label of this vertex to Bob, which is log n bits, and she sends an indicator vector of length n that indicates the entire out neighborhood of this vertex from her perspective. What Bob does, he sends back an indicator vector to Alice with his out neighborhood of this vertex v. So at this point, what has happened? They both know a vertex v. They both have full information of the out neighborhood of v because they've communicated this over here. And moreover, you know that this vertex has at least n-1/4 out neighbors. So what they do is they just eliminate the out neighborhood at this point, recurse on the in neighborhood, and use the same thing again, recurse. And this is not very hard to see that, again, you get some sort of geometric sum, or you can use the master method if you're lazy like me. So each iteration here costed log n for
The master method.
sorry.
It's just method of solving equivalences, right? Which can master.
Yeah, so you just unpack that is.
So okay,
Yeah. I mean, it's if you look up CLR.
Exactly.
The recurrences of the form A T of n is equal to A T of n by P plus.
Was there a template for it?
Yes.
Yes. So instead of unpacking manually, you can just invoke this template. Yeah. So usually you would unpack it. This just gives you a textbook. So yeah, if you have T of n equals A T of n over B plus C, then you compare A log B with n to the C, I think. N power A log B with. Yeah, okay. Anyway. We can look at examples later. But hopefully it's clear. Like in order n cost, you've reduced your vertex size by a constant. And if you want to work it out using a geometric series, the total cost of this protocol will be order n. Is this protocol okay? Questions?
Basically, in 2 steps, they understand the entire outcome.
Yes, the 2 steps meaning order and cost though, because they're exchanging this entire out neighborhood information. So you might say, I mean, is there, can we do better? And as a spoiler, I'll already tell you that we show matching lower bound. So we have omega n as well. And I'll sketch at least a lower bound proof towards the end. All right, now let's go back to source finding, the more maybe natural definition of a tournament winner. And let's say the problem over here is Alice and Bob. Again, Alice has some edge directions, Bob has some edge directions, the other ones. And they want to know whether there exists a source in the underlying tournament. So what Alice can do is she can look at her edge directions and conclude some potential sources. So clearly, if Alice sees these edges, she knows that V2 cannot be a source in the entire tournament because already V1 to V2 is an edge. So from her point of view, all of these 3 vertices can be potential sources. From Bob's point of view, V1 could be a source. He has no information about it, or V3 could be a source as well. If you think about it, there's either 0 or 1 common potential source. If there were 2, this would mean that this would mean some contradiction. It's very simple if you think. Can I ask how many of you have seen communication complexity? Some flavor. Okay, good.
You cannot do this.
Sorry?
You need omega n to do this.
No, you can do it better. I was hoping already this will give some indication if you
Constant. You're finding the sink or source with the log n.
Not yet. Maybe soon and not log n. You'll see. Hopefully,
No, I mean, I'm sorry, I misunderstand. So you're asking if Alice and Bob to find a source if there is one.
Yeah.
Or say there is no.
Sure. Yes.
There is no there.
Let's see a protocol and a lower bound that contradicts your log n.
Noted in the letter.
Click versus independence.
Yes.
Yeah.
Click versus independence is log square.
Oh, log square, sorry.
Yeah.
Forget the log.
Yeah.
Log square, yeah. It's exactly click versus.
Yes. So we will see that soon. Yeah, you're right. So here's a protocol. You can do much.
This is something we had observed in our field.
That this is the same as click versus independence. This I don't remember.
This
I have to
we
go back.
call source sinks.
Yeah. I'll need to go back and check it.
Anyway.
Okay, so here's a protocol. Again, we're going to use Morer's lemma over here. What Alice will do is she checks if she has a potential source with large out degree. So with out degree at least n-1/2. If yes, she just sends the label to Bob. Bob checks if this is a source from his perspective as well. And if both of these fire, then they found a source. Okay, all good. But let's suppose this yes doesn't fire, or any of these cases don't fire. Bob checks if he has a potential source of large out degree. If he has sends it to Alice, she checks if this is an overall source, and then they found the source. So suppose any of these checks fail. So that means a vertex, let's say this, sorry, I mean, this check I really intend to be the internal checks over here. So let's suppose Alice found a source from her perspective with large out degree, at least n-1/2. She sends this information to Bob, which is log n bits. And Bob says, no, this is not a source from my perspective. So for this vertex V, you can eliminate all of these n-1/2 out neighbors. And then use essentially Morer's lemma. So if this check fails, Alice and Bob know that all vertices connected from V are out neighbors from Alice's perspective.
I think this is the anarchist protocol,
Yes.
not forest law.
Um,
In our community, we call it the anarchist.
sure,
But
but
findings.
yes, but I don't think it's been. This is essentially click versus independent set protocol.
Completely this.
Yeah, but it's not from this perspective. I'm just presenting it from a directed tournament perspective. Yes, this is exactly Yanakakis' protocol from the early 90s for the click versus independent set protocol. Problem. But basically, if either of these two checks fail, then you've eliminated n-1 over 2 vertices, which were an out neighbor. Sorry. And if both of these fail, then you can check that there's no source. Just sorry for not explaining it very well. We'll skip ahead. If there's more time later, if there are questions, I can come back to this. So what happens in this protocol is at each step, either Alice sends log n bits to B, maybe Bob sends log n bits. Alice sends log n bits to Bob. Bob potentially sends log n bits to Alice. If they found a source, they found a source. Else, they've eliminated at least half of the other vertices, recurs on the in-neighbor. So you get log n iterations with log n communication per iteration. The total cost is order log square. And yes, if you've seen some basic communication complexity, you'll realize that this is essentially the click versus independent set Yanagakis protocol. Order log square n is a strange number that I've only seen associated with click versus independent set.
Also appears in the space in.
Okay. I'm sure it appears in data structures and so on, but
And then what's this?
savages.
Yeah, savages.
Possible. Okay, but in the context of communication complexity. Right. So again, a spoiler, this will turn out to be tight as well, essentially. Right. So for a lower bound for kings.
Nikhil, is there a general reduction from clique versus independent set to this question, or?
Yes. So we will, in fact, we show that they're equivalent. It's not extremely hard to see it, but yeah.
It was like this for click versus independence, it was established just reverse.
Yes. Yeah. So we just show the equivalence of this problem, or observe the equivalence of this problem with CIS. Yeah. Right. So coming back to kings, let me just put the slide up again here. So we saw a few slides ago a cost order n protocol for finding a king. And now I'll sketch a lower bound proof that matches this order n protocol. And we show a reduction from permutation max finding. So we introduce this function. This is, I think, a fairly natural function. Somehow we didn't see it studied in the past. So in this function, Alice is given a ranking of n elements. Equivalently, you can think of as a permutation on n elements. Bob is given a subset of elements, and their goal is to find in Bob's subset which is the highest ranked element of Alice. So what's a trivial protocol? Alice can simply, well, Bob can simply send his subset over to Alice with n bits, and Alice sends the label of the highest rank, log n bits. And it turns out that you can't do any better than this. So we're able to show a reduction from set disjointness to this problem. And set disjointness has well known to have communication complexity omega n. Right. So what we're going to do is now assume this omega n lower bound for permutation max finding. Again, the problem is Alice is given a ranking of n elements, Bob has a subset, and they want to know within that subset what's the highest ranking. So I'll warn you on the next slide, there's going to be a bunch of arrows and text and all, but we can go a little slowly. Don't be thrown off, please. So here's the sketch of the proof. Alice and Bob are now given an instance or input to this PMF problem, this permutation max finding problem. And they're going to convert this locally into an instance to finding kings. And then I'm going to argue here that if they can find kings, any king in this tournament that they jointly locally constructed, this will give them the answer to PMF. Okay, this is the sketch. Okay. And maybe I can even tell you how the construction works. So Alice is given a ranking, Bob is given a subset. So this joint tournament that they're going to construct is going to be on 3n many vertices. So each blob over here has n vertices. And for those n vertices, let's say, so each of these n vertices are labeled from 1 to n, and the same over here and the same over here. So Bob constructs all cross edges between the blobs just based on his set. Alice constructs all internal edges within the blobs based on her ranking. So this gives all of the edges in this tournament. And now, okay, I'm not going to get into full details, but what it's going to turn out that there's going to be exactly 3 kings in this jointly constructed tournament, 1 in each blob. And the label of these kings in each blob are precisely going to be the solution to PMF on sigma ns. So they're going to be the highest ranked elements of sigma in each of these S's over here. So if they can find a king, so they've either found this king or this king or this king, but regardless, the label of that king is actually the answer of PMF on sigma comma s.
So all 3 kings will have the same label.
Yes. So if they can find a king here, they've solved PMF. And this reduction used zero communication, it was all local. So because of this omega n lower bound that I told you on the previous slide for PMF, this means finding kings also has an omega n lower. Questions? So I'll tell you very quickly about some other results that I didn't talk about at all and summarize our work. As Arkadev has been pointing out, we observed that source finding is essentially equivalent to this clique versus independent set problem, which is well studied in communication complexity. And this means whatever order log square n protocol I sketched to you earlier is essentially tight. So there's some lower order log terms. So there was an extensive line of work that ended up in this matching lower bound for the clique versus independent set problem. Like I mentioned, a maximum out degree vertex in a tournament is also a king. So you could ask, what about considering the communication complexity of finding a maximum out degree vertex? And we do that, and we have essentially tight bounds in deterministic, randomized, and quantum. So in a preprint of ours, we had an upper bound of order n log n for the randomized complexity and a lower bound of only n, omega n. Then we were told that the lower bound should actually be stronger. So this bound is in fact tight. So it's interesting that the deterministic and randomized bounds are off by this lower order log term. Right. So to summarize, at least in the query complexity setting, where complexity of kings has most been studied. There's a complexity upper bound of order n to the 3/2. And I want to emphasize, by the way, that this is not just an artifact of the query setting. So this complexity is really the time complexity of finding a king as well. So there's really not much overhead that an algorithm does apart from queries in this setting. Yeah, so you can find a king in an n-vertex tournament in time order n to the 3/2. And there's a query lower bound of omega n to the 4/3. And we showed tight randomized and quantum bounds for this last year. And at least for me, the most interesting open problem that still remains is, can we close this gap? I'm still not sure what bound to expect. So in this work, what I showed to you today, or what I talked about today, is the communication complexity of finding a source in a tournament, which is equivalent to the clique versus independent set problem, and the communication complexities of finding the king in a tournament. So in all these settings, we have essentially tight bounds up to log factors. And with that, I'll stop. Thank you.
I was thinking, suppose you have many kings and you have to select one of them as a winner. One way to do it would be to have some way of defining a distribution on those things and then sampling from it.
Okay.
What sort of distribution should I consider here? What would be a good distribution to?
How do you choose among multiple kings? And then once the same, let's say your distribution over kings, what should your distribution look like? In one way, you could think is maybe just the out degree also, right?
But there would be kings of the same order.
Maybe from the same out degree, yeah, sure.
So one way would be just pick one uniformly at random. Yeah. Is there something else that is capturing some structure we're going also?
Well, the question is, does some king capture the structure of the government, or?
The question is open-ended. This is what sorts of distributions? How would you choose a winner if you have to actually give somebody $1 billion? Then which one would it be?
The one who solves P versus N.
Actually, in your setting for communication complexity, if you want to find a king of max degree, just go through.
If you want to find a max degree vertex, then ask.
For max degree, your bounds are larger, yeah.
But you're saying you want to find the maximum degree among kings.
Yes.
But this is interesting that Umang points this out. This is indeed larger than finding kings by a slight margin. In the query complexity setting, the gap is much larger. Yeah, but I don't know if you have multiple kings, how you would type it. Even our randomized upper bounds, I don't think we come up with any clean distribution on the kings.
How is this, sorry, this is great, you can call it sugar data. I'm just curious, how do you show, obviously the most interesting natural question is the first one.
Yeah.
Yeah, like, a very natural question, what is the query complexity of finding a king?
Yeah.
Yeah. And so how does this lower bound into the 4/3, into the 3/2 I see sort of.
Maybe for the benefit of all, I'll quickly sketch the end of the 3/2 because it's not very hard. So we want to use Maurer's lemma again. So essentially, I want to find a vertex that has very large out degree.
Better, talk is formally. So maybe we should take it off. Or
I think
take it online? Yeah.
Like, you still find.
Yeah, sure.
Unless you're going to say something that you don't want to hear.
No, I'm fine being.
That will be it.
So
Yeah,
Yeah, go ahead. So there's your 3 by 2.
yeah. So I want to find a vertex that has large out degree,
Yeah.
and I want to eliminate that out neighborhood. So what you can do is you pick root n vertices arbitrarily. And now this choice root n, you can play around with it, but root n is going to turn out to be optimal. So arbitrarily pick root n vertices, test all edges between it, in that induced subtournament. So you've queried order n edges. Now by counting, you found a vertex that has out degree at least root n over 2 or root n minus 1 over 2. So now this vertex, I'll find its entire out neighborhood in the entire tournament. So now I've guaranteed that you have this vertex that has out degree at least root n over 2. I spend order n queries. So in order n queries, you can reduce the vertex set. So order n queries.
Master.
You drop the vertex set by an additive root n.
It's not master method, it's just clean.
Yeah, So essentially, you repeat this root n times, you get n to the 3 over 2, and of course, there's calculations to work out, but this works out. For the n to the 4 over 3 lower bound, you define an adversary. And the adversary definition is also fairly straightforward. So the adversary will answer edge directions in the following way. If an algorithm queries vertex u and v, then the sorry, you were pointing there. I was pointing. So if the algorithm just checks the out degree of u currently, out degree of v currently, and directs it from the lower out degree to the higher out degree.
Yeah, I was thinking, it seems natural, but I don't see how the number 4 by 3 helps.
Wait, I didn't follow. So what is the adversary?
So you just like equalize the output.
Vertices?
Or maybe prioritize vertices that have smaller out degree. You can afford to give more out degree. So let's say at some intermediate point in the tournament, I have the algorithm has figured out this and this, right? And now the algorithm is queried. Sorry, the adversary is queried. What is the direction between this? So it's going to check the out degree of. So first of all, if it just note that if you answer in this direction, this vertex is already a source. Okay.
So you basically always put that to the lower, the person who has the lower degree.
Yeah.
For him to-
So this currently has out degree 0. This currently has out degree 2. So you direct it from the lower to higher.
Minus the 0 into the 4.
Yeah, that is what I don't.
Okay, so that I don't think I'll be able to reconstruct the whole proof, but I can give you a rough sketch. So let's suppose that an algorithm at the end finds a king V. So look at all of its neighbors in order in which these edges were revealed by the adversary. So let's suppose this has out degree D in the end. And out of these D edges, suppose this was the first to be revealed. I can't guarantee anything here. But for the second edge to be revealed, now if this was answered in this direction, that means this vertex must have already had out degree 1, right? Because at this point, this vertex already had out degree 1. Similarly, what you'll be able to say is that over here, this vertex must have already had out degree D minus 1. So if V has out degree D, then you must have made omega D square queries. Now you can say the same about the each of the neighbors here. And now there's some small but clever argument where you can combine both of these and you get into the fourth. Okay, now you can ask that argument I won't be able to reconstruct right now, but it's fairly small.
And that's type, so there is no hope of, this
Yes.
adversary, the natural adversary cannot yield you an into the 3R.
That's correct. So in one of these works that I mentioned earlier by Biswas et al., they actually showed that this is in the beginning of my talk. So it's Biswas, Jayapal, Raman, and Sati. So their work, they actually show that for this adversary, you can design an order n to the 4/3 cycle. And that's also not very hard actually. Yeah, so you need to come up with a better adversary.
So did you start trying to solve this problem first and then realize that it is related to sequence independent set, or did you? I don't know.
No, we were trying to solve the communication problem, and then we came up with this log square and upper bound, and then we were suspicious with the protocol and the log square n itself, and then we realized there's just equivalence. Yes. But this whole study of kings itself, I mentioned it at last year's FSTTCS. I don't know how many of you were there. It's very interesting. 2 years ago at FSTTCS, I attended a talk on kings in tournaments. I asked an open question. I asked a question to the speaker at the end. The speaker didn't know the answer.
Who was the speaker?
Chaya Trehan.
Okay.
And me and collaborators, we answered that question, published it next year's FSTTCS. And this is a follow-up of that, which appeared in Random this year.
Were you asked any questions?
I don't think I was asked open questions.
So I have a quick question. So in the source finding communication problem, are there, I mean, I don't know if this is a well-formed question, in the sense that like there are ways of partitioning the set of edges between Alice and Bob, right? I mean, like do we know what are bad partitions versus good partitions? Like obviously, if Alice owns some vertices and Bob owns some vertices in some sense, then finding a king would just be easier, right? Like if each vertex was owned by one of the two players and they have all the out degrees, then it becomes very easy.
Yeah.
So is there a notion of what is a hard partition in some sense?
I have not thought about this. So, by the way, the equivalent question in clique versus independent set would be in the underlying graph, like what is a hard graph, basically.
Right.
And I don't know if this has been studied. I mean, I guess the clique versus independent set question has been studied much more than this. Even there, I don't think people have thought about this. I don't know.
No, like for instance, if the edges were randomly partitioned between Alice and Bob, is that already a hard instance?
Yeah, I'm not sure about that. This lower bound is only existence and also
Okay.
convoluted. I don't think there's a. Yeah, I don't have an answer. Sorry.
Okay, next FST.
Next PI part. More questions? Let's thank Nikhil.